action of heat on compounds. There are many chemical compounds present in nature. Due to the great number of these compounds, we will concentrate on the compounds of group 1 and 2 elements. Group 1 elements include lithium, sodium, potassium, rubidium, and cesium, while group 2 elements include beryllium, magnesium, calcium, strontium, barium, and radium. We will first look at what happens to some of the compounds on heating. Group 1 compounds are more stable to heat than their corresponding compounds in group 2. You will often find that the lithium compounds behave similarly to group 2 compounds, but the rest of group 1 are in some way different. We will begin with heating the nitrates of group 1 and 2 compounds. Most nitrates tend to decompose on heating to give rise to the metal oxide brown fumes of nitrogen dioxide and oxygen. For example, a typical group 2 nitrate like magnesium nitrate, the NO3 on the line is the formula for nitrates. So, when magnesium nitrate is heated, it will give rise to magnesium oxide plus nitrogen dioxide and oxygen. In group 1, lithium nitrate behaves in the same way. Therefore, when lithium nitrate is heated, it decomposes to give rise to lithium oxide plus nitrogen dioxide and oxygen. The rest of the group, that is from sodium to cesium, do not decompose so completely, at least not at Bunsen temperatures, that is, the temperature of a Bunsen burner, producing metal nitrides and oxygen, but no nitrogen dioxide form. Therefore, if we have a nitrate of group 1 element other than lithium, represented as thus, the X stands for the other group 1 elements, but not lithium. This nitrate decomposes when heated to give rise to the nitrite and oxygen. no nitrogen dioxide is formed. All the nitrates from sodium to cesium decomposes in this same way, the only difference being how hot they have to be to undergo the reaction. As you go down the group, the decomposition gets more difficult and you have to use higher temperatures. We will proceed with heating the carbonate. Most carbonates tend to decompose on heating to give the metal oxide and carbon dioxide. For example, a typical group 2 carbonate like calcium carbonate, the underlying CO3 is the formula for carbonate. Therefore, calcium carbonate on heating decomposes to give rise to calcium oxide and carbon dioxide. In group 1, lithium carbonate behaves in the same way, producing lithium oxide and carbon dioxide. The rest of the group 1 carbonates don't decompose at Bunsen temperatures, although at higher temperatures they will. The decomposition temperature again increases as you go down the group. We will now talk about the thermal stability of the hydrogen carbonates. The group 2 hydrogen carbonate, like calcium hydrogen carbonate, are so unstable to heat. They only exist in solutions. An attempt to get them out of solution causes them to decompose to give the carbonates carbon dioxide and water. Calcium hydrogen carbonate, the underlying HCO3 is the formula for hydrogen carbonate. When heated, it decomposes to give calcium carbonate plus carbon dioxide and water. By contrast, the group 1 hydrogen carbonates are stable enough to exist as solids, although they do decompose easily on heating. For example, sodium hydrogen carbonate will decompose to give rise to sodium carbonate plus carbon dioxide and water. Now, let's carry out an experiment to determine the change in mass when a compound is heated. In order to better understand this experiment, let's consider the element magnesium. Magnesium is weighed and then heated in a crucible. This magnesium reacts with oxygen to produce an oxide known as magnesium oxide. It can be shown that there has been an increase in mass. The result can be used to find the formula of magnesium oxide, and the method used is described below. The practical activity can take 30 to 45 minutes depending on the competence of the students. Students should all be standing and should wear eye protection. Students with long hair should tie it back. In order to carry out this experiment, there are some basic requirements. We will need an eye protection per pair or group of students, crucible with lid, tongs, Bunsen burner, pipe clay triangle, a tripod, a heat-resistant mat, and an emery paper. The procedure is as thus. Cut a piece of magnesium about 10 to 15 centimeters long. If it is looking tarnished or black, then clean it using the emery paper. Twist it into a loose coil. Weigh the crucible with the lid and record the mass as mass 1. Then weigh the magnesium inside the crucible with the lid and record the mass as mass 2. Set up the Bunsen burner on the heat-resistant mat with the tripod. Place the pipe clay triangle over the tripod, ensuring that it is secure. Place the crucible containing the magnesium in the pipe clay triangle and put the lid on. Light the Bunsen burner and begin to heat the crucible. It is best to start with a gentle blue flame, but you will need to use a roaring flame with the air hole fully open to get the reaction going. Once the crucible is hot, gently lift the lid with the tongs a little to allow some oxygen to get in. You may see the magnesium begins to flare up. If the lid is off for too long, then the magnesium oxide product will begin to escape. Don't let it happen. Keep the heating and lifting of the lid until you see no further reaction. At this point, remove the lid and heat for another couple of minutes. Replace the lid if it appears that you are losing some product. Turn off the Bunsen burner and allow the apparatus to cool. Reweigh the crucible with the lid containing the mass 3, that is that of the product. Heat the crucible again for a couple of minutes and once again allow to cool. Repeat this step until the mass readings are consistent. This is called heating to constant mass. The setup is as does. Note: students should have recorded the following masses. Mass 1, which is that of the crucible plus lid. Mass 2, which is that of the crucible plus lid plus magnesium. And mass 3, which is that of the crucible plus lid plus product. This should allow you to calculate the mass of magnesium, which is given by mass 2 minus mass 1, and the mass of the product, which is given by mass 3 minus mass 1. They could also calculate from this the increase in mass, which is given by mass 3 minus mass 2. This increase in mass corresponds to the mass of oxygen. The equation is thus: magnesium plus oxygen to give rise to magnesium oxide. Students sometimes get unconvincing results to this experiment. It is worth evaluating what they have done, as there are several reasons why the results may be disappointing. It may be due to the magnesium oxide product, which might have escaped as they lift the lid, or not all the magnesium may have reacted. The product may still look a bit gray rather than white. Now, Let's find out the formula of magnesium oxide. To find the formula of magnesium oxide, students will need the mass of magnesium, the mass of oxygen. You will also require the relative atomic mass of magnesium, which is 24, and that of oxygen, which is 16. Then you will divide the mass by the atomic mass of each element. This gives the number of moles. The number of moles of each element is equal to the given mass, which is gotten from the experiment, divided by the relative atomic mass of each element. Having done this for both elements, you should find the ratio between the two by dividing both by the smaller number. The ratio should be close to 1:1, as the formula of magnesium oxide is MgO. Example of the calculation. Mass of magnesium as gotten from the experiment is 2.39. That of magnesium oxide is equal to 3.78 grams. Therefore, the mass of oxygen will be equal to 3.78 minus 2.39, giving us a total of 1.39 grams. Now, to get the number of moles of magnesium, we'll proceed as thus. It will be equal to the mass of magnesium, which is 2.39, divided by the relative atomic mass, which is 24, giving us a total of 0.0995, while the number of moles of oxygen will be equal to 1.39 divided by 16, giving us a total of 0.0868. Between 0.0995 and 0.0868, which is the smaller. You will agree with me that the smaller is 0.0868. Following the instructions, we need to divide the number of moles by the smaller one. Therefore, we will divide 0.0995 by 0.0868, and we divide 0.0868 by 0.0868. The first division gives us an answer of 1.15. 1.15 is approximately equal to 1, and the next calculation gives us an answer of 1. Therefore, magnesium and oxygen combine in a ratio of 1:1, thereby suggesting the formula of magnesium oxide to be Thanks for your kind attention.